We are up to Wednesday, August 10th for Math 1324. We're going to be finishing up week 4 homework today. Okay, so week 4 homework. Okay, so that number 29, I made just a slight calculation error early in the problem and it threw the whole thing off, so let's maybe do 30 as one more example of that. Okay, so we're going to turn this system into an augmented matrix. Okay, this is number 30. So you got 7, 23, 5. 7, 23, 5. And then going down, it's 16, negative 2, 9. Three, 10, 4. 1, 3, negative 3. So we're trying to get, let me put it over here, 1, 0, 0, 0, 1, 0, 0, 0, 1. And then if we do that, then the answers are right here, X, Y, and Z, or X1, X2, and X3, however you want to label it. So first goal is to try to get a 1 right here. And normally what you would do is if there's a 7 there right now, you can divide everything in this row by 7, because 7 divided by 7 will be a 1. Now, unfortunately, that often gets messy because you'll have 23 over 7, 5 over 7, 16 over 7, but sometimes you don't really have a choice. But one thing that's nice is because there's a 1 right there, I could interchange the first and third rows. If I interchange the first and third rows, then I've got the 1 in the slot we need it to be. And then nothing happens to the second row. So that got me, at least I avoided having messy fractions right away. But there's the 1 in the first slot. So that's 1 step down, 8 to go. Next we need zeros here and here. Always go down and do that whole first column first. So the key is the 1, because anything times 1 is itself. And what I want to have is the opposite of this 3 and the 7. So the opposite of 3 is negative 3. Negative 3 times 1 is negative 3. Negative 3 times 3 is negative 9. Negative 3 times negative 3 is positive 9. Negative 3 times 9 is negative 27. Add these two together. And this will create a new row 2. 3 minus 3 is 0. There's the 0 that we want. 10 minus 9 is 1. 4 plus 9 is 13. Negative 2 plus negative 27 is negative 29. So I changed row 2 and got the 0 right here that I wanted. And then, except when you're interchanging 2 rows, you only change 1 row at a time. So I can rewrite the first and third rows. And now we got 2 out of 9 steps down. 2 down, 7 to go. So just like up here where I did the opposite of 3, negative 3, now I need the opposite of 7. The opposite of 7 is negative 7. So if I multiply the row where the 1 is by negative 7, then I'll get my opposite that I need. Negative 7 times 1 is negative 7. I'll put it right down here. Negative 7 times 3 is negative 21. Negative 7 times negative 3 is positive 21. Negative 7 times 9 is negative 63. Add these two rows together and you'll have a 0 in the bottom slot. I'll put it up here. So this 7 minus 7 right here, that's 0. 23 minus 21 is 2. 5 plus 21 is 26. And double, see, this is what I did wrong last time, is I assumed I could do that in my head, but 16 minus 63, you're better off just do it in a calculator, make sure you get it right, because if you miscalculate, I had a brain cramp. I got negative 14 when it was actually supposed to be negative 20. 16 minus 63 is negative 47. If you do make a mistake anywhere along the way, then unfortunately everything after that's wrong. And you won't know it till the end, really. So I changed row 3. That means the first two rows are not changing. So rewrite these first two rows. 1, 0, 3, 1, negative 3, 13, 9, and negative 29. So we normally would be 3 steps down, 6 to go. Again, we got a little bit lucky that there's now a 1 right here like we needed. The next thing you do is you go after this 1 right here. You always do 1s first. So I get this 1, and then I need these 2 zeros after that. So again, if that was not already a 1, I would just divide everything in that row by whatever it is. If that was a 6, I would divide everything by 6. 6 divided by 6 would be 1. But I got the 1 there, so now we need this 3 and this 2 to both become zeros. So same deal, you always want to work with the row where the 1 is, and you want to do the opposite of whatever one you're doing. So the opposite of 3 is negative 3. Negative 3 times 0 is 0. Negative 3 times 1 is negative 3. Negative 3 times 13 is negative 39. Negative 3 times negative 29 is positive 87. Add this to the first row and you'll get a 0 in that slot you're hoping for. So the new first row would be 1 plus 0. See how that 1 didn't change. Negative 3 plus 3 is 0. Aha. Negative 39 and negative 3 is negative 42. 87 plus 9 is 96. Rewrite the other two rows. And now we need a 0 where that 2 is at the bottom. This 2 right here needs to be a 0. So I'm going to multiply the row where the 1 is by the opposite of the 2. The opposite of 2 is negative 2. Negative 2 times 0 is 0. Negative 2 times 1 is negative 2. Negative 2 times 13 is negative 26. Negative 2 times negative 29 is positive 58. Add these two together. This will make a new third row. 0 plus 0 is 0. 2 minus 2 is 0. Now we got a little lucky here. 26 minus 26 is 0. And then negative 47 plus 58 is 11. Rewrite the first two rows. So normally at this point you would be 6 steps down, 3 to go, and you would try to make this a 1 next. And after that's a 1, then you'd get these two to be zeros, and then you would be done at that point, and there would be 1x equals whatever ended up here. It wouldn't stay at 96, but it would change. And then 1y would equal this number, and then 1z would equal that number. But if in the process of doing this you get an entire row of zeros, then you get either no solution or infinite solution. So this is like in systems saying that the whole left side is 0, and the right side is 11, 0 does not equal 11, that's no solution. If you get 0 equals 0, then infinite solution. But usually this can become a 1. Only if this was 0 would this happen. So I was almost finished doing the whole process, but then it ended up being a no solution. But that's generally the idea. You just keep doing that over and over again, and get your 1s first, then your 2 zeros, then get the next one, get the 2 zeros, get the next one, and get the 2 zeros, and hope that you don't have any slight calculation errors like me. So there could be a unique solution. If you get 1, 0, 0, 0, 1, 0, 0, 0, 1, then there's a unique solution. X, Y, Z, or X1, X2, X3. If you get all row of zeros and anything other than a 0 on the other side, that's no solution. And then infinitely many solutions. Okay, so I don't think you'd pick this C ever. So then it would be B if that were to happen. And then we just let the third one equal some variable like t. And then we write these two in terms of t. Is why that's an option. I think they just needed a fourth option for that other one. Okay, so at least you got to see a little bit more of that since I messed it up last time. 41, now we're in a different section, and this will definitely go quicker on this problem. Find both the opposite or additive inverse and the reciprocal or multiplicative inverse of the following number. So additive inverse and multiplicative inverse are different concepts. And it depends what you have for the original number, but if you have the number 5, the additive inverse is what do you add to that so that you get the identity of addition, which is 0. And 5 plus negative 5 adds up to 0. So this is called the identity. And this is the additive inverse. Negative 5 is the additive inverse to positive 5. But in multiplication, it's 5 times what gives you a 1 for an answer. 1's the identity of multiplication, and that's the reciprocal 1 over 5. So an additive inverse is the same number, just the opposite sign. The multiplicative inverse is the same sign, but it's the reciprocal where you do 1 over, you flip it. So the opposite, and they call the additive inverse the opposite, they call the multiplicative inverse the reciprocal. So the opposite of negative 3 over 11 is positive 3 over 11. You don't change the number, you just change the plus and minus. And then in the reciprocal, it's the opposite. You don't change the sign. A lot of people think the reciprocal of negative 3 over 11 is positive something, but the sign stays the same in the multiplicative inverse. You flip the fraction, 11 over 3. But if the original is positive, the answer is positive. If the original is negative, the answer is negative for a reciprocal or multiplicative inverse. So what we're going to build up to is the inverse of a matrix. So if you want something to be an inverse of a matrix, what would need to happen is the original matrix times the possible inverse would have to have an answer that went 1, 0, 0, 1 if it's 2 by 2, or 1, 0, 0, 0, 1, 0, 0, 0, 1 if it's 3 by 3. And it's a diagonal of all 1s, and everything else has to be a 0. This is the identity of matrices. So that's what it takes. Now, they're asking if you start with 9, 3 as your original matrix, does the given matrix have a multiplicative inverse, and explain your reason why? Well, the one choice says yes, because this matrix is it. None of the other choices have that, but It literally cannot be this because both of these matrices are 1 by 2. And if you do a 1 by 2 times a 1 by 2, that's not even possible to multiply that, because the inside dimensions have to match. So for sure the answer is not A. A 1 by 2 could never have another 1 by 2 as its multiplicative inverse. To really, in a matrix, in order to have an inverse, you have to be a square matrix. So if you have a 1 by 2 or a 2 by 1 or a 4 by 3 or anything that's not a square matrix, it's not possible to have an inverse. So this is really the reason. If the original is not a square matrix, then you don't even need to worry about it. There is no inverse. Now this is a 2 by 2. This is a square matrix. So does this have an inverse? In theory it could, but when we go looking for the inverse of a matrix, here's what happens. At least for 2 by 2s. In 2 by 2 we do what's called a determinant. The determinant tells you, it determines whether you can get an inverse or not. That's why they call it determinant. In a generic matrix A, B, C, D, the determinant, which they abbreviate DET a lot, is A times D minus B times C. So for this one, it would be 0 times 0 minus 0 times 0, which is 0. If the determinant is anything except for 0, any positive or any negative, then you can find an inverse to a square matrix. But if it's 0, there won't be an inverse, because the first step you're going to do is 1 divided by the determinant. And 1 divided by 0 is undefined. So this will not have an inverse because the determinant is 0. Okay, so this is, again, let me show you this quick back here. If you do something in math and an operation and you take its inverse, whatever the inverse happens to be, the answer is an identity. But what an identity is if you take anything in math and do the identity to it, an identity keeps you exactly the same as you started with. So 0 is the identity of addition because anything plus 0 is the anything. 1 is the identity of multiplication because anything times 1 is itself. So a matrix, if it's 2 by 2 and you multiply by 1, 0, 0, 1, it will equal itself. Or if it's 3 by 3 and you multiply by 1, 0, 0, 0, 1, 0, 0, 0, 1, it'll equal itself. So that's why in problem 44, they say find the following product, but note the product can be found mentally without doing pencil and paper calculations or even a calculator. This is an identity matrix right here. So any identity times any matrix is the any matrix. So you're going to get that other matrix no matter what. So click the matrix tab. And these are all 3 by 3, so the answer is going to be 3 by 3, 3 by 3, and just retype this second matrix. And for identities, it's the same. Whether the identity matrix is first or second, you'll get the other matrix no matter what. So 44 is an easy problem. That's the point of it. An identity matrix times another matrix is the other matrix. Now, are these inverses of each other? We haven't learned how do you find an inverse yet. So one thing we could do is let's just multiply these two like we did yesterday. And if I get, since these are 2 by 2s, if I get 1, 0, 0, 1, then yes, they're inverses of each other. But if I don't get that, they're not. So 45, my first 2 by 2 matrix is -3, 2, -2, 1. The second one is 1, negative 2. 2, negative 3. A 2 by 2 times a 2 by 2 is possible because the inside dimensions match. And then the outside dimensions are the size of the answer. We're going to get a 2 by 2 answer. And all we really care about is it 1, 0, 0, 1, then yeah, then these are inverses of each other. So if any slot I don't get the 1 or 0 I'm looking for, then we can stop. So remember, you use the rows of the first matrix and the columns of the second matrix. Negative 3 times 1 is negative 3, plus slide and drop, 2 times 2 is 4. Negative 3 plus 4 is 1, so far so good. Now do row 1 with column 2. Negative 3 times negative 2 is positive 6, plus 2 times negative 3 is negative 6. 6 plus negative 6 is 0, so far so good. Now do row 2 with first column 1. Negative 2 times 1 is negative 2, plus 1 times 2, which is 2. Negative 2 plus 2 is 0, that worked. And finally, row 2 with column 2. Negative 2 times negative 2 is positive 4. 1 times negative 3 is negative 3. 4 plus negative 3 is 1. So yeah, these are inverses of each other because when I multiplied them, I got the identity matrix. That's how you say yes to this. Now you're not going to want to do that every time you're looking for an inverse because it could be a lot of guessing and checking to find it. So there is a way to find the inverse directly without relying on another one. And then the symbol for that is m with a little negative 1. That doesn't mean that's not 1 over m. It's not the negative exponent rule. It looks like a negative exponent, but that's just the symbol for inverse. So an inverse of a 2 by 2 is not too hard to do. For a 2 by 2, you find the determinant first. If you get 0 for the determinant, you can stop and say there's definitely no inverse. So negative 2 times 12 is negative 24. Now, when you're multiplying matrices, it's always plus between the calculations, even if the calculations themselves are negative. So I do negative 3 times 1 plus 2 times 2. It's always plus. But in the determinant, it's always minus. So you could get that mixed up in the middle of a test. But it's always minus. Now you may be doing minus a 25 or you may be doing minus a negative 25. This one's minus negative 25. But if both of these were 5s, it could have been minus 25. So if it's a double negative, then it does switch to plus. Otherwise, it stays minus. Negative 24 plus 25 is 1. The determinant is not 0, so therefore there is an inverse. And to do the inverse, what you do is you do 1 over the determinant times, you remember how the generic one goes A, B, C, D. The A and the D switch places with each other. The B and the C stay where they are, but you get the opposite, the additive inverse of them. And then you distribute this into everything because it's scalar multiplication. But if the determinant's 1, then you're going to get 1 over 1, which is 1. And 1 times anything is the anything. So if the determinant's 1, then all you're going to do is the inside of this. So I need to switch A and D around with each other. They don't switch signs. The negative 2 right here goes down to the bottom where D was. The positive 12 goes up to where the negative 2 was. And then you switch -5 to +5 and switch 5 to -5. And again, if it was anything other than a 1, you'd have to distribute that in. So this is the inverse matrix right here. And if you were on a test, you could double check it. You could take this original matrix times this answer, and it should equal 1, 0, 0, 1, the identity matrix. But it takes a little while to check that, so I'm just going to put the answer in. It's a 2 by 2. 12 and 5 for the top row. And the bottom row was -5 and -2. Okay, so similar deal on 47. I got a 2 by 2, -5, 15, -4 and 12. So the determinant is -5 times 12, -60, minus -4 times 15 is also -60. There's a double negative here. There's not always a double negative, but if there is, it turns into plus. -60 plus 60 is 0. I'm not going to be able to get an inverse because I'm going to have 1 over 0 times, and then you do your magic inside the matrix, but 1 divided by 0 is undefined. There's nothing to distribute in. So if the determinant's 0, you can just stop and say the inverse matrix does not exist. It also doesn't exist if you don't have a square matrix. So those are the 2 times you don't get an inverse of a matrix. Okay, so 48 should work. (48) 2, 3, 3, 3. So 2 times 3 is 6. Minus 3 times 3 is 9. The determinant's -3. So the inverse, I'm going to do 1 over the determinant. The 2 and 3 here interchange with each other. You don't change their sign, you just interchange them. These 2 3's stay where they are, but you have to do the opposite, so they would both turn to -3. And then you have to distribute this in. -1/3 times 3 is literally 3 over -3, which is -1. And then this one will be +1. This one will be +1. And this one doesn't reduce. You just get 2 over -3, or what would be -2/3. So if I did the original matrix times this one, you would get 1, 0, 0, 1, and you would get the identity. So the inverse is -1, 1, 1, -2/3. 2 by 2. -1, 1, 1, -2/3. Okay, so this one's similar, 49. The original matrix is -5, 0, 0, -3. So the determinant is -5 times -3 is 15, minus 0 times 0 is 0. That's not a double negative, although 0 is not really positive or negative, but that's just 15. So it's not 0, it's 15, so there is a determinant, there is an inverse, 1 over 15. And then I'm going to interchange these two, but they're going to both stay negative. -3 and -5. These two stay where they are, and they're technically supposed to turn to negatives, but there's no such thing as negative 0. So 1/15 times negative 3 is literally negative 3 over 15. And then you should reduce that down. Both of those divide by 3. So negative 1/5. Anything times 0 is 0. Anything times 0 is 0. That's why it doesn't matter if you say minus 0, really. And then 1/15 times negative 5 is negative 5 over 15. Those both divide by 5, so negative 1/3. So this would be the inverse of the original one. So just because it has some zeros in it doesn't mean that the answer is no inverse. Maybe that they were maybe thinking somebody's going to see these zeros here and think, oh, there must not be an inverse. In fact, they don't even give you an answer to put no inverse exists. So it's a 2 by 2 matrix, and I got negative 1/5, 0, 0, and negative 1/3. Whoops, didn't register right. Okay, gotta delete that 0. There we go. Okay, so 3 by 3. The process is a little different for 3 by 3. Here's what you do. The original matrix is 1, negative 1, negative 1. Zero, negative 2, negative 1. Negative 8, negative 9, and 0. And now you're going to see why we did problems 29 and 30. So over here on the right of the matrix, you write the identity version 1, 0, 0, 0, 1, 0, 0, 0, 1. The goal here is to turn the original matrix into this. And while you're doing it, this stuff will change. So we got to go through our 9 steps again, although here they were, I guess, going easy on us a little bit. There's already a 1 here, and there's already a 0 there. So we just need this to be a 0 next for that column. And it's currently a negative 8, so if I multiply the top row by positive 8, then I'll get 8, which is the opposite of negative 8. And then I'll get negative 8, negative 8, 8 times 1 is 8, and 8 times both of these zeros is 0. Add these two together, and that's going to make the third row become 0, negative 17, negative 8, keep going, 8, 0, and 1. And remember, you only change one row at a time, so we still have 1, negative 1, negative 1, 1, 0, 0, 0, negative 2, negative 1, 0, 1, 0. So we've got 3 slots down, 6 to go. Next, you want to get a 1 right here. So for the first time since we've been doing these, there isn't a, oh, we didn't get lucky to already get a 1 there. So it's easier to get 1s than to get 0s. If you want a 1 in a given slot, you just divide the whole row by that number. So if I divide this whole row by negative 2, and one thing that's also true is once these become 1s and 0s, they never change. The other ones might change, but the ones you're finished with, the great thing about the process is they never change back. It's never like, oh no, I got to go back and do those again. So you're not going to change the first 2 rows. Let me write them down. Now here I don't have enough room to do a lot of them on the same screen. 1, negative 1, negative 1. 1, 0, 0. The bottom row is 0, negative 17, negative 8. This definitely helps to have a lot of convenient scratch paper. 8, 0, 1. Okay, so we're dividing everything by -2, but 0 divided by anything is 0. So this 0 and both of these, they're going to stay 0. And -2 divided by -2, that's the whole reason we're doing it. That's 1. Unfortunately, the other two get messy. -1 divided by -2 is +1/2. And this +1 divided by -2 is -1/2. But we got 4 down, 5 to go. Next, I want this -1 here to be a 0. And it's already the opposite of +1. So I don't need to multiply the 1 by anything. It's already opposites. Add these two together. And that'll be your new top row. So the new top row is 1 plus 0 is 1. -1 plus 1 is 0. -1 plus 1/2. See, that's where it gets a little harder, but that's -1/2. 1 plus 0 is 1. 0 plus -1/2 is -1/2. And 0 plus 0 is 0. Rewrite the other two rows. So now we got 5 down, 4 to go. The next goal is get this to be a 0. It's currently a -12, so I'm going to multiply the row where the 1 is by the opposite of this -12, which is +12. 12 times 0 is 0. 12 times 1, there's the 12 I want. Half of 12 is 6, at least that came out nice. 12 times this 0 is 0. 12 times -1/2 is -6. And 12 times 0 is 0. Add these two together, and that'll be your new third row. So 0 plus 0 is 0. -12 plus 12 is 0. -8 plus 6 is -2. Notice we didn't get a 0 there like that, problem number 30. 8 plus 0 is 8. 0 plus -6, and 1 plus 0. Rewrite the first two rows. So 6 down, 3 to go. On that problem number 30, we were done at this point because we had a whole bottom row of zeros. So next we need this to be a 1. And it's easier to get 1s than getting 0s. You just divide everything in that row by whatever it is. Anything divided by itself is 1. So -2 divided by -2, that'll turn that into a 1. And 0 divided by anything is 0, so these zeros are not going to change. The new bottom row is going to be 0, 0, 1. 8 divided by -2 is -4. -6 divided by -2 is +3. And 1 divided by -2 is literally -1/2. Rewrite the first two rows. So 1, 0, 0, 1. Try to do the easy parts first. -1/2 and +1/2. Got a 1, 0, and 2 -1/2s. And 2 zeros. So 7 down, 2 to go. We just need both of these to be zeros and we're done. So you always work with the 1. 1 times anything is the anything. So what I want it to be is 1 times the opposite of this. The opposite of 1/2 is -1/2. If I multiply everything where the 1 is by -1/2, then I'll get opposites there and I'll get the 0. And anything times 0 is 0, so you get 2 zeros in front. Negative a half times 1 is negative a half. Negative a half times negative 4 is positive 2. And unfortunately, the other two aren't nice, but negative 1/2 times 3 is negative 3 halves. And negative a half times negative a half is positive 1/4. Add these together. Nope, I'm sorry, I pointed at the wrong one. This one and where I circled it. Because I want the negative 1/2 and the positive 1/2 to cancel and make 0. So we're getting a new row 2 here. The new row 2 is going to be 0 plus 0. Notice it didn't change, 0. 1 plus 0 didn't change, it's still a 1. And then literally right here, that's where 0 happens. But I got to keep going. 0 plus 2 is 2. At least this will come out evenly. Negative 1/2 plus negative 3 halves is negative 4 halves, which is negative 2. And 0 plus anything is the anything, so 1/4. Only row 2 changed, so the other two rows don't change. And now we have 8 slots down, 1 to go. Only thing left, this has to be a 0. It's currently negative a half, so the opposite of that is positive a half, and multiply the row where the 1 is by the opposite, positive 1/2. A half times 0 is 0. A half times 1 is a half. Half times negative 4 is negative 2. A half times 3 is literally 3 halves. And 1/2 times negative 1/2 is negative 1/4. Add this to the first row, and then you'll get the 0 right here. So 1 plus 0, this is the new first row. 1 plus 0 is 1, and 0 plus 0 is 0. Notice those two didn't change. So I've got 1 and 0. They never change once they become 1s and 0s. And then here's what I wanted. Negative 1/2 plus 1/2. That'll give me a 0 there in that slot. That's what we wanted. So 1 minus 2 is negative 1 for that slot. Negative a half plus 3 halves is 2 halves or 1. 0 plus negative a fourth is negative a fourth. And now just rewrite the other two rows. And this part's easy, 0, 1, 0, 0, 0, 1, because that's what we were trying to do. I've got a 2 and a negative 4 here. A negative 2 and a 3. And a positive 1/4 and a negative 1/2. Once you get the identity right here, we started way back here, and we had not the identity in this slot, but the identity was over here. Once we manipulated stuff so that the identity moved from here to over there, then the stuff that was here became new stuff over there. This is the inverse right here. Once you get the left side to be the identity, then the right side, notice it's all different numbers than it was originally, the right side is the identity matrix. That's how you do 3x3s. So this is too long to see on a test. You're not going to see this on a test. It just takes too long. But it's good to do this one time. And now it relates to those other problems 29 and 30 that I messed up number 29 on yesterday. Okay, so it's negative 1, 1, and negative 1/4. Negative 1, 1, and negative 1/4. Assuming I didn't make any calculation errors. 2, negative 2, and positive 1/4. And inverses often have fractions in them just because it's the only way to make it come out to the identity. -4, 3, and -1/2. And big bucks, no whammies. Oh, one of my responses is incorrect. Okay. Unfortunately, when that happens, it's going to be time consuming to go back and figure out what it was. How close was I? Oh, I was way off. I might be forgetting one step because obviously all the answers are way different. Maybe the determinant plays a role too. Let me check that real quick. Okay, so here it's going to take them a while to get it to change. Okay, see, right there they did it. They got 1 0 0 0 1 0 0 0 1, and they got all this. You have to do anything to that? No, huh? Something went wrong early on apparently. 5 5 1, yeah. That should, I thought that was it. So once you start like this, you just slowly and methodically get your 1 here, then 0. So next, they already had that at the start like we did. So they had to change this to a 0 first. We did that. Then you get the 1 right there in the middle. Then turn both of those to 0s. They did the top one first, and then they did the bottom one second. Then you get a 1 right here. And now you turn both of these into 0s one at a time. They did the top one first, the bottom one second. And the fact that I have fractions in mind, so there must have been a mistake somewhere in there. So that should have worked, I messed up somewhere. So I'll look for my mistake, but first thing to check is, did I even write the problem down correctly? 1 -1 -1, 0 -2 -1, -8 -9 0. Yeah, okay. So yeah, I'll have to look at this. I don't want to waste time in the video searching all this. Must be one small calculation error, and since every answer was way off, it must have happened early on. But I'll do that after the video's over and let you know what happened to 50. And like I said, this one's not on the test, but it's good to see this and see I'm even messing these up myself. It's real easy to have one small error in there somewhere, and once you do, it throws everything off. So I'll have to look for that when I have more time. But at least that you've seen that process now a few times. And I messed it up 2 of the 3 times already. Okay, so here's the final section of the week. We're doing section 4-6 here. And this seems like from the past. I don't know why they're showing this now, but it must be related to whatever this section's about. But here's an easy problem, 51. This is like high school algebra right here. 6 minus 4x. 6 minus 4x equals 6x minus 8x plus 4. So if you have a 6 and a 4x on the same side of the equation, they don't go together. Same thing with this 8x and this 4, but these two are what we call like terms. They're on the same side of the equation, so you can combine them together, just as they are. 6x minus 8x is negative 2x. But when you're on opposite sides, like terms, you have to do the opposite to get them together. So I would add 4x to each side, because I like the x to come out to be positive. You can do it the other way and get a negative x, but then there's an extra step at the end. So this way, negative 2x plus 4x is positive 2x. Minus 4 to get those like terms together. 2x equals 2. Divide by 2, and x equals 1. So 1's the only number that we can plug in to the original problem, and both sides of the equation would be equal. If you put a 1 here, you would get 6 minus 4, which is 2. And if you put 1's here and here, you would get 6 minus 8, negative 2, plus 4, that's also 2. So that's why 1 is the solution. It's the only number that makes both sides equal to each other. Okay, so I guess we're doing some algebra with matrices. So this is just multiplying. Let me write this out so you see what's happening here. 52. I've got a 2 by 2 matrix. 4, -2. 2, 3. And then times xy equals -2, 4. So if I multiply these two matrices, remember you use rows of the first one and columns of the second one. So you would get 4 times x plus -2 times y, or just minus 2y. And then that would equal this. Because we're doing a 2 by 2 times a 2 by 1, so the answer is a 2 by 1. So the answer we're getting doesn't even go together, but it will match the answer of this side. So it's literally changing this back to a system of equations. 4x minus 2y plus a negative, or minus 2y, that has to equal the -2. And then do the same thing with the other row. If I do row 2 with the only column that's here, you would get a 2 times x, 2x, plus a 3 times y is a 3y, and that would have to equal this 4 right here. And this is a system like when we did the substitution, elimination, all that stuff. So these things go back and forth between each other. And 2x plus 3y has to equal 4. Whoops, they already had the equal 4, sorry. So they put that there already, just I guess to let you know what to do. So then you could solve this with substitution or elimination like before in the previous chapter. Same deal here. So you're just going to go across here while you're going down this one, and you'll get an equation. Literally 1x, or x, plus a -7y, or minus 7y, plus a 4z. That's going to equal -3. And this time they didn't put the equal, because you're doing a 3 by 3 times a 3 by 1, so the answer is a 3 by 1 like this one. This is literally the answer slot. So second equation is doing row 2 with the only column, -3 times x, and then plus a -8y, or just minus 8y, and plus a -8z. That has to equal the middle answer of 3. And finally, 4x minus 7y plus 7z has to equal the 2. So those, you're not even solving anything, you're just writing it. Okay, now they want me to do the opposite. So they already put the x, y, z in essence from all the variables. So on this box, you need a 3 by 3 matrix from all these numbers. This is exactly the reverse of the last two problems. So the numbers are all, you don't have to do any calculating. It's all right here. Just reading this is all you're doing. 1 for the 1x, and -2 for that part, and then +6. And then there's a -2, a +4, and if it's blank, it's literally a 0. You know, there's sometimes zeros inside the matrix. And then 1, 1, 5 for the bottom row. And that'll equal your x, y, z, and then this answer is your 3 by 1 right there. So I need a 3 by 1. 3 by 1, and it's literally -3, +1, and -6. So again, all you're doing is translating these back and forth. Okay, so find x1 and x2, okay? So now notice they're in the answer slot. They're not right here. Normally they were like right here. So if we multiply this out, we're going to end up with a 2 by 1, and that's what these would match up to. So what number are we on? This is 55. So whether you put the x1 and the x2 here, or you could put it way over on the right side, that would be the same thing. So there's a 2 by 2 matrix, 3, 2, negative 1, 2, times a 2 by 1, negative 2 and 1. So I use the row of row 1 of the first matrix and the only column of the second matrix. 3 times negative 2 is negative 6, plus 2 times 1 is 2. That answer is negative 4. So this would be a 2 by 1 answer, and the first answer would be negative 4. And then I use row 2 along with column 1. Negative 1 times negative 2 is 2, plus 2 times 1 is 2. So that's 4. So in other words, this negative 4 is this x1, and this positive 4 is this x2. So that's what x1 and x2 are, negative 4 and 4. But if they're here, they're in a different slot now. So now you're better off just writing this as a system and solving it. So negative 1, 4, negative 1, 2. And again, you can think of this as x and y, or x1 and x2. That's synonymous. And then this is negative 27 and negative 17. So this will be negative 1x plus 4y. Remember, slide and drop. That has to equal the negative 27. We did this like 3 problems ago. And then negative 1x plus 2y. That has to equal negative 17. And then you could do substitution elimination from the previous chapter. I could multiply this by negative 1, because then I would get positive 1x, negative 2y, and positive 17. Add these two together. Negative 1x and positive 1x would cancel. 4y minus 2y is 2y. Negative 27 and 17 is negative 10. Divide both sides by 2. Y equals negative 5, or if you want to call that x2, the second x is negative 5. That's this answer right there. And then you can plug this negative 5 back into any of the original problems. I would probably plug it in right there. Negative 1x, or just negative x. 2 times negative 5 is negative 10. That would equal negative 17. Add 10 to both sides. Negative x equals negative 7, so positive x must be positive 7. So this is similar to the previous chapter where we were getting coordinate answers like 7 and negative 5 for the x and the y. That's what they're literally doing here, is they're trying to relate how the system method from the previous chapter and this matrix method are really the same thing. It's just 2 different ways to do the same thing. And even in the previous 3 or 4 problems, you can translate back and forth. If you like the system method better, translate to a system and solve it like this. If you like the matrix method better, then do that. It gives you options that you can do. So the x1 is 7, and the x2, or what is similar to saying the y in the previous chapter, that's negative 5. These are just 2 lines across each other at one point. Okay, here I could use some matrix operations first and then repeat what we just did on 56. So I've got a 2, 3, negative 2, negative 5. Then there's the x1 and the x2, or x and y. But then what's different on 57 is there's a plus 4, 1, 2 by 1 matrix. Equals 29 and negative 30. Well, we could just subtract this matrix from both sides, because then you would have a 2 by 1 minus a 2 by 1, which is a 2 by 1. And just like in algebra, these would cancel out. So that would leave you with 2, 3, negative 2, negative 5. Equals 29 minus 4 is 25, because you just do the similar ones. Negative 30 minus 1, be careful about that. Negative 30 minus 1 is negative 31. And then you could set up two equations, two unknowns, and solve it with substitution or elimination. Another thing you can do too is, this is a 2 by 1. I guess, no, you can't do that. I was thinking 2 by 1 times a 2 by 2. Well, what if we put it in front? Yeah, here's something you can do. This probably would take longer, but you can do this. This is a 2 by 1. If I found the inverse of this, what's the inverse of 2, 3, negative 2, negative 5? This 2 by 2 right here. The inverse of that, we just learned inverses. You would find the determinant first, negative 10 minus a negative 6. So that would be a double negative. That would turn into a plus 6. Negative 10 plus 6 is negative 4. So the inverse is 1 over the determinant. You interchange these two, but keep their signs. The 5 stays negative, the 2 stays positive. The 3 stays there, but you do the opposite, negative. The negative 2 stays there, but you do the opposite, positive. And then you distribute this negative 1/4 in. So the inverse is positive 5/4, positive 3/4. This would be, both of these would be negative 1/2. So what that does, you know how in algebra you like divide by this thing to get, if you have like 3x equals 6, you divide both sides by 3, because those are inverses of each other. So moving this to this side of the equation so that you have x1 and x2 isolated, that works if you do the inverse on the other side. So if I were to put 5/4, 3/4, and negative 1/2 and negative 1/2, if I remembered all those correctly, 5/4, 3/4, negative 1/2, negative 1/2, times this 25 and negative 31, this will produce the answer as well. This will be a 2 by 2 times a 2 by 1, which is a 2 by 1. This is probably harder because you have to find the inverse first, and now you still got to multiply. I need to do this row times this column. But since I'm almost at the answer, I'm going to go ahead and finish it this way. It would have been easier after doing this step right here to just do it with substitution or elimination. But watch how this should give us the same answer. So 5/4 times 25. 5/4 times 25 is 31.25. And I better write that down somewhere. 31.25. Plus, that was this times this, plus slide and drop, 3/4 times negative 31. is negative 23.5. So now add that to 31.25, and that's 8. So now do the second row times the only column. Negative a half times 25, or what would be the same as 25 divided by 2, negatively. Negative 12.5. And then half of negative 31. Negative 31 divided by negative 2 is positive 15.5. Add that to negative 12.5. That's 3. So the answer should be 8 and 3. So this is even another option. You can do 8 and 3. And it would have been the same if I would have done it with a system too. This is the same problem as 57. You just have to add this to the other side. So I'm not going to do this one fully out, but let's set up what you would do. So you got your 2 by 2 first. 9541. You got your x1 and your x2. This time there's a minus 2 by 1 matrix instead of a plus. 8 and 9. And then the answer is supposed to be 14 and 6. So just like last time, you can add this matrix right away because it's just easy to add things. Adding matrices is easy. That's the additive inverse right there. So 14 plus 8, you just add the similar parts. 14 plus 8 is 22. 6 plus 9 is 15. So now you got two choices. You can either write a system out and have 9x1 plus 5x2 equals 22, and 4x1 plus 1x2 equals 15 and solve that. That would work. Or you could find the inverse of this, 9 minus, it's not going to be nice either. The determinant's 9 minus 20, that's negative 11. So definitely the system would be the better choice here. 9x1 plus 5x2, that would equal 22. And 4x1 plus 1x2, that would equal 15. And you could easily multiply this by negative 5. Negative 20x, 1. There's negative 5x2. And that's negative 75. Add these two together and the x2's will cancel. Here's this negative 11 again, like the determinant. 9 minus 20 is negative 11. 22 minus 75 is negative 53. So maybe these aren't even coming out evenly. Divide by negative 11. X1 would be 53 over 11. Whoops. See, type integers are fractions, so they must be coming out as fractions. 53 over 11 is the first answer. So getting the second answer is going to be harder with a fraction, but I could plug it into 53 over 11. We could plug it in right here where the numbers are all positive and smaller. So you would have 4 times 53 over 11 plus this x2 would equal 15. 4 and 53, they don't reduce by 11, so 53 times 4 is 212 over 11. 212 over 11. I don't think that divides out. Let me make sure. Yeah, see, that's a messy decimal. Plus x2 equals 15, or 15 over 1. And then you would need that one over 11, so multiply it by 11 over 11. That would be 165 over 11. So subtract 212 over 11 from each side. And that way, x2 equals whatever this is, 165 minus 212 is negative 47 over 11. So these came out really messy, and if I did the inverse matrix idea, it would really be messy because the determinant was negative 11. But see how it worked because of that? So there would be a bunch of fractions in that other method too. That would make it hard. Okay, what do we got here? Write the given system of equations as a matrix and solve using inverses. Okay, so now they want me to, what are x1 and x2? Okay, oh, they're giving me numbers there. That's weird. Why don't they just put the numbers in there? But see, this is again a case where if you did it the normal way, nobody's going to know you did it this way. So negative 2x1 plus 3x2. For some reason that equals 10, and they're telling me separately, instead of just putting a 10 there, they're told it to me separately. They said if k1's 10, why don't they just put the 10 there? Negative x1 plus 2x2. That one equals 10 also. They want you to create a matrix and do it that inverse way that I just did 2 problems ago. So they're looking for this, where you get the determinant first, and then you move this the other side with the inverse. If you put the inverse right here, then you can just multiply these matrices together. But this would be real easy to do with elimination. I could multiply this by negative 2, because negative 2 times negative 1 would be positive 2. And then I would get negative 4 and negative 20. Add these two together. The 2 x1s would cancel. 3 minus 4 is negative 1 of those. And 10 minus 20 is negative 10. Divide by negative 1, x2 is positive 10. And that's just a coincidence that that 10 was the same as these 10s. And then I would plug that into, I guess this middle equation would be best because they both have 10s. 2's a little smaller than 3, and negative 1's a little smaller than negative 2, and there is an equation with all positives. So negative x1 plus 2 times 10 equals 10. Negative x1 plus 20. And I don't think this is always how it works out, but this is going to be weird how this comes out to 10 also. Because this is negative 10 right here. And then if you divide by negative 1, it switches back to positive again. So I think that was just a coincidence. Also, they were trying to make a point here. They're both 10s then. But I don't think the answers are both 10 just because these were both 10s. So I just did that with a system instead of doing, okay, see how they changed it now? Okay, so what if they were 9 and 2 instead of 10 and 10? Negative 2x, I don't think the answers are going to be 9 and 2, but let's see. Plus 3x2. What if this was 9? And see, this is where the system helps a lot, because if we did this the way they intended the problem, this would take like 20 minutes to do this problem. Negative x1 plus 2x2. Come on, go. So again, I'm doing the same step because that's what it's needed to be the opposite. This will be 2x1, and this is your negative 4x2. Although this part will be different, that's negative 4. So add these two together again, and the x1s cancel. You still get a negative x2, but now you get 5 there. So x2 is -5, and it's not a 2. So that's my point, is just because this is 9 and 2, that's not what your answers are going to be. Somehow when these were both 10s, these were both 10s, but when you have a 9 and a 2, I got a -5 for this one. And then plug the -5 right there. So -x1 plus 2 times -5, that'll equal 2. So -x1 minus 10 equals 2. Add 10. -x1 is 12. So positive x1 is -12. So this time we got completely different answers. Positive, what did I say, -12? -12. So I'm not sure what the point of doing this twice was. And then they're doing a third one? Whoa. So why did they keep doing this over and over again? I'm just going to get these wrong because we've already done it twice. Negative, I guess they just drill and kill. They're making you do that 3 times for some reason. So there's no real pattern to this. I had 5 and 1 the third time, and the answers were -7 and -3. I would never guess that, but so I'm not sure why they're making you do that 3 times. And then what's here? Okay, so the matrix equation is not solved correctly. A inverse B. Explain the mistake and find the correct solution. Okay. X times A. Okay, so I know what's going on here. This is trying to show what I did right, this idea right here. And what I was first thinking was, this is a 2 by 2 right here. And if you do the inverse of it, the inverse will be 2 by 2. But you can't just put this wherever you want. At first I was thinking, what if I put it here in the back? But that wouldn't be good because then the inside dimensions wouldn't match. And it actually turns out that if you have matrix A times X equals matrix B, in order to move this matrix A over to the other side, what you're literally doing is in front, you're doing an A inverse in front. So then you need to do it in front on this side too. You don't do it in front here and in back over there, because in matrices, multiplication order matters. Then these would cancel each other out, and X would equal the inverse times B. That's what I ended up doing on that problem. Where was it? So I found the inverse of this, and I placed it right in front. The inverse times this, that's what the X is equaled. That's what they're hoping you'll do on problems 57, 58, and 59, to do this method. But if the inverses take a while, first of all, and then if they come out fractionally, then this method gets really hard. So at least you can still solve it with a system. But the point they're making on number 60 is, if you have X times A equals B, you can't place the inverse of A, you can't place that in front. That's what they're trying to do, is this. Because that's what you do here. That's what you're getting used to the pattern. But the issue here is this is reversed. And these will cancel out when they're next to each other. They don't cancel out when there's an X in between them. That's the problem. So what you really should do to solve this problem is you need to put the A inverse back here, which means it would be on this side of the B, then it will cancel out. So it's order is very important here in matrices. It's not, we already saw that before when we were multiplying. When you do matrix A times matrix B, it's not the same answer as potentially as B times A. In fact, sometimes A times B is possible and B times A is impossible. In fact, that's what happened to me on this problem when I was first thinking about putting that inverse back there. So it makes a difference. So that's what 60, you're not doing anything other than noticing that. Okay, so they don't have what I did here, but I'm noticing you could do this too. if you put a x inverse instead of an a inverse, if you wanted to put that in the front, you could. But usually the goal is to solve for x, so that doesn't sound right. Matrix A should have been subtracted. Definitely not. This is all multiplied together. The equation should have been multiplied by inverse of B. That really wouldn't get the x by itself. Mix the left. Yeah, see, it's this. This is it. Mix the left multiplication property and the right multiplication property. In regular numbers, that doesn't matter. If you have 3 times x equals 6, you can multiply by a third. On either side, it doesn't make a difference. Order doesn't matter. Whether I do this or this, it's the same thing. But in matrices, it matters. Putting the inverse on the left side is not the same as putting it on the right side. That makes a difference. So, and you need them to be next to each other for them to cancel too, is the other idea. So you can't just put it left or right and kind of ignore that. You got to pay attention that you do it the same to both. So the correct solution should be what I said, is put the A inverse right there on the right-hand side of that side, so then you need it on the right-hand side of this side. So your other side should be capital B and then A inverse. And it's not technically an exponent, but it looks like an exponent. So you still hit the exponent toolbar, but it's technically not an exponent. It's not 1 over A. Okay, so I did, I skipped the last part of 59, but I did 2 of them, so I could have got that right if I would have spent the time doing it. And I missed 50. I got to go back and figure out what I did wrong on that one, because the answer was totally wrong. So I must have messed up, but I did all the exact steps they did, so there must have been a slight calculation error early on. So I'll try to find that, and I'll email it to you what went wrong on that problem. Where did it even start? Here it was. Okay. So I'll research that. It might take me a while to figure out what went wrong there. But at least you got a good idea of the rest of this homework, and you'll be all good for the review and the test for sure. So that's it for Wednesday, August 10th for 1324.